Okay, so this is net force example number 2. And I have 4 forces, and these forces are described a little bit differently so that we can draw what they would look like and then use our knowledge of cosine and sine, adjacent and opposite, to determine whether or not we have how to calculate our horizontal and vertical components. So I threw in a little bit of different descriptions for these types of forces. When we do force problems, you might get descriptions like he's pushing down and to the left at 10 degrees with respect to the horizontal. And how do we visualize that? How do we draw that? And then how do we analyze it? So this is going to approach that a little bit. And so I have 4 forces. We're going to draw them in a representation that we call free body diagram. And then we will take that representation and we will do the net force with our vector addition. So 11 newtons at 45 degrees is force number 1. So first I'm just going to put on our coordinate system down here, and we have 45 degrees as in quadrant 1. So our force number 1 is going to be in that quadrant, and here is theta 1. And so I'm not to kind of alleviate a little bit of the clustering or the cluttering in my free body diagram, I'm just going to represent the forces as angles and force numbers. All right, so force number 1, and there is its representative angle. Force number 2 is 5 newtons at 35 degrees west of north. So how do we look at that? Well, north is our up axis, our positive y-axis. West of north is going to be on the side that's in the negative x direction. So 5 newtons, 35 degrees west of north. So here's force number 2. This is angle 2 that we're determining. So the 35 degrees is in relationship to the positive, the north axis. All right? Force number 3, 15 newtons at negative 35 degrees. So without a reference given, it's always relative to the positive x-axis. So we have 15 newtons at negative 35. That is in our third quadrant. So here's force 3, and this is our angle 3. All right, so 15 newtons at negative 135. And then finally, force number 4 is 8 newtons at 50 degrees south of west. So here's our west, our negative x-axis. South of that is going to be relative to that negative x-axis. And so we have force number 4. And this is our angle 4 as given in the problem. So south of west. All right, so those are the 4 forces as represented on what we call a free body diagram, where all of the arrows are represented on a single coordinate system. And a true free body diagram is going to have our object as a representation in the middle of that coordinate system. So just to give you a little preview of that free body diagram stuff. All right, so how do we add these forces together? Well, we want to keep in mind that we are dealing with vector algebra, so we have to look at both the horizontal and the vertical components of each force. Add those horizontal components, add those vertical components, get the horizontal and vertical component of the net force, and then put it back together in a single representation. So let's do that. Force number 1. That angle is given with respect to the positive x-axis. So for horizontal, I use cosine. Vertical, I use sine. And we have 11 cosine of 45. And vertical, 11 cosine, sine of 45. All right, so our calculation of 11 times the cosine of 45 is 7.8 newtons. And although we should probably be able to do this one in our heads, if I've already done one, confirming that the sine is also 7.8 newtons. All right, they're both positive. They should be. I'm in quadrant number 1. Okay, force number 2. Force number 2's angle is given to me with respect to the positive y-axis. Now, there's a lot of different ways that you can do this. You can add 90 degrees to that and do it with the positive x-axis, and then have 5 times the cosine, 90 plus 35, 125. And 5 times the sine of 125. So I've just added 90 degrees to my 35 so that I have an angle with respect to the positive x-axis. Okay, and then it's cosine and sine. We don't have to do it that way. We could also use this 35 degrees and recognize that the horizontal component is opposite the angle. Opposite is sine. So we could also do a 5 times the sine of 35 degrees. And 5 times the cosine of 35 degrees. Now I'm going to erase one of these so as not to get confused, but I want to show you what it looks like. So if I plug in 5 times the cosine of 125 degrees, I get an answer of negative 2.9. And 5 times the sine of 125 gives me 4.1. If instead I've looked at that angle that was provided for me, I have the calculation of 5 times the sine of 35, and I get positive 2.9. 5 times the cosine of 35 gives me positive 4.1. What do we notice? Well, we notice that the magnitudes are the same. Good, the components should have the same magnitude. But the signs are not. And so if we were to look at the top example, it will always give us the appropriate sign if my angle is with respect to the positive x-axis. If I don't use the angle with respect to the positive x-axis and I pay attention to the interior angle, we call the interior angle, and make the triangles and do the appropriate sines and cosines, I have to be very explicit about the sign. I have to say, okay, well, I am pointing to the left, so my horizontal component has to be negative 2.9. And I am pointing up, so my vertical component is appropriate as a positive 4.1. So either one of these options, these methods, is appropriate. Either one is fine. You have to do the one that you're most comfortable with. Sometimes adding that 90 degrees or adding the 180 degrees or 270 degrees, depending on your angles, can be confusing. Sometimes remembering that we have to be very careful about that interior angle can be more challenging. So whatever works for you is fine, as long as you are being attentive to the sines and the cosines and using them appropriately and the direction that the component needs to be. Okay, so I'm going to use the lower one in this example. So I'm just going to erase this so as not to add it accidentally. I'm going to move my 2 down. All right. Okay, so let's look at force number 3. Force number 3 is given with respect to the positive x-axis. So I have 15 times the cosine of negative 135 and 15 times the sine of negative 135. So 15 cosine of negative 135 is equal to negative 10.6. And 15 times the sine of negative 135 is also negative 10.6. Should have been able to do that one in my head. All right. So both are negative. I'm in quadrant 3. Both should be negative. Last but not least, we have force number 4. Force number 4 is 8 newtons, 50 degrees south of west. So this is what I'm looking at. I'm going to use that same method of using the angle given to me as I did in force number 2. So south of west, my horizontal component is adjacent. So I have 8 times the cosine of 50 degrees. My vertical component is opposite, 8 times the sine of 50 degrees. So 8 cosine of 50 is 5.14, but I'm in quadrant 3, so that needs to be a negative. I'm going to be explicit about putting in my negative 5.1. 8 times the sine of 50 gives me 6.1, but again, I'm in quadrant 3. I think I said quadrant 4 back here. Quadrant 3, so I need to be concerned about my direction. It needs to be a negative 6.1. So I'm putting in those negative values because I'm not using the angle with respect to the positive x-axis. My calculator is just going to give me the magnitude of that component, and I have to be explicit about the direction. Okay, so now I have all of my components. I can add them together. So my horizontal, the sum of the forces, horizontal is going to equal 7.8 minus 2.9, minus 10.6, minus 5.1. And I get a total of negative 10.8. My vertical components are 7.8 plus 4.1 minus 10.6 minus 6.1, and I get a sum of the forces vertical is equal to negative 4.8. All right, so these are my two components. So to get the magnitude of the sum of the forces, I take the square root of negative 10.8 squared plus negative 4.8 squared, and I get an answer of negative 10.8 squared plus negative 4.8 squared, 11.8 newtons, and that is consistent with my answer. And then I want to get the angle as well, so I take the inverse tangent of negative 4.8, the y component, over negative 10.8, the x component, and I get an angle of 24 degrees. That's in the first quadrant. Both my components are negative, so I need to be in the third quadrant. So I add 180 degrees to that, and I get 204 degrees for my angle. All right, so again, representing those angles in different ways is going to be important for us to be able to do. Utilizing that information to be clear about our components if we choose to use an angle that is not with respect to the positive x-axis. Splitting them up, adding those components together, and then putting it back together as magnitude and direction for the net force. All right, good job.